And the last one for this afternoon is Susan Graham. Susan Graham was one of the first women, I don't think the first, but close, to get her PhD in computer science from Stanford, and she's been a professor of computer science at Berkeley since 1971. She is she was sort of the major force behind the ACM transactions on programming languages for 15 years. She's a fellow both of the Association for the Advancement of Science and of ACM. And she's famed, I think, for her contribution to almost every aspect of programming languages. Now, when I was looking for a good story to tell you about Susan, I couldn't find any stories nearly as spicy as the ones I was able to uncover about the previous speaker, as she alluded to, but I've been sworn off those. What I was able to find out, I repeatedly heard stories about the fact that this is a person who is extraordinary and caring in her mentoring, and that she has mentored many different women didn't think I'd find out, huh? At every stage of their career. I'd like you to welcome Susan Graham.
Thank you for that very nice introduction. Just one point I wanted to correct, if I may. To my knowledge, the first woman to get a PhD in computer science from Stanford was Barbara Liskhoff, who was my colleague and my TA when I was at Stanford. I realized when I was coming here on the plane that the first talk I ever gave at a conference was in exactly this position in the program. I was the last speaker in a full day of talks, and my talk was at 5 o'clock or something like that. Only that time it was my first talk, and I spent all day getting very, very nervous about that talk. And about 3 years later, I was talking to a friend who was on the program committee, and I said to him, I hope you never do that to a graduate student again, because they get very nervous. And he said, well, the reason that we put you in that position on the program was not accidental. We thought about it very carefully. This was a theoretical computer science conference. He said, you were the only woman on the program. And we figured if we put you at the end of the day, then we could hold on to the audience for the rest of the day. So I'm very pleased to know that whatever the reason is that I'm at the end of the day, that's not what it is. What I want to do today is to talk to you about language implementation from the point of view of the kinds of problems that I've worked on. And so this is not a general survey in any sense. And in fact, it's not really me, it's us, because most of the work that I've done in collaboration with my graduate students. And so all of the ideas that I'm going to touch on that were work that I was involved in are work that we did, and if I say I, you should hear that as we. Now, in fact, when I use the word language, what I really have in mind is something closer to programming languages than the kinds of languages that Karen was talking about this morning. What I'm really talking about, as you'll see, are languages that are formal languages in some sense, that have formal descriptions, and therefore about which one can do a certain amount of analysis and a certain amount of manipulation. And I'm going to divide my talk, survey if you can call it that, into two parts. In the first part, I'm going to be talking about formal language translation. You can read that as compiler construction to a large extent. And in that part of my talk, I'll actually be very indebted to the introduction that Fran Allen gave this morning. She was kind enough to prepare you for many of the things I'm going to talk about. And then in the second part of my talk, I'm going to turn to what, loosely speaking, I'll call software understanding. And I discovered to my pleasure that both Mary Shaw and Irene Greif had prepared you in ways that I'll illustrate for the ideas that I wanted to show you in that part of my talk. So let's start with the transparencies. I have to tell you that I originally thought I was going to do my own transparencies. Then I noticed this morning that people were standing up here and having other people turn their transparencies. So I switched, only to learn that Dorothy Denning was doing her own, and I figured I'm not going to switch back again. So let's look at the problem of program translation. I've given you a very little program, and I've given you a very high-level outline of the job of a translator, a compiler, or even an interpreter. It takes a source language program, and it goes through a sequence of steps, all of which, roughly speaking, have to do with analyzing the program in order to get some sense of what it's about, what it says, some of its properties, and from the results of that analysis, synthesizing that same computation in some other representation. And if you think about what Fran was showing you this morning, she used those ideas over and over again. And if one has multiple phases, then at each stage, one analyzes the current situation, asking certain questions, and then synthesizes some more information, resulting in the case of compilation in a target language. So I've now got a target program down there in which what the program does is it increments a register which is holding the value of the variable sum. Now, as Fran pointed out to you, that basic structure is something that's been used from the very beginning. That's the structure that John Backus used in 1957. One can go back before that and see that that's the structure. So why is it that 35 years, 40 years later, there are still interesting issues? And let me try. Fran brought out some of these points, but let me give you my own take on it. One of the reasons that there are continuing challenges is that languages keep changing. If you think about the role of language, programming languages and other higher level notations are human notations. And we want them to be readable by people. We want people to be able to reason about them. We want them to express the things they want to say. The translation problem is to take that high-level, readable, understandable specification of a computation and map it down to an efficient execution on a piece of hardware. And there's a continuing tension between the properties that the people need and the properties that you need in order to carry out the translation. And as we get new languages, those problems continue to occur. As compiler writers, we have to deal with what we arrogantly call blunders in language design. Namely, there are people who don't get the human needs right. There are people who don't have a good sense of how you do the mapping that takes you to a machine. And people keep designing new languages, and so these two forcing functions keep coming up. I can make very similar remarks as a software person about computer architecture. That the other side of the mapping problem is that we have to map onto existing hardware. And what hardware or computer architects are doing over time is trying to make their machines faster and faster, or sometimes cheaper and cheaper. And in order to do that, they make design choices that are legitimate from that perspective, but which cause us to have additional problems on the other end. I could make the same remark I've made a little more gently about computer architects, that they're not perfect either, and to the extent that they make bad design choices, the compiler writers in the middle have to solve the mapping problem all over again. Finally, because the machines are changing and the languages are changing, there are continual new challenges for us in taking old languages and putting them on new machines. Fran gave you just a glimpse of what happens when you take Fortran programs and try and put them on parallel architectures. Similarly, there are new languages in which the underlying language design assumptions don't map to old machines. For example, we normally feel in doing language design that we can afford to use a lot of space in the translated program. There are still machines in which space is a commodity that one has to conserve. And then the final reason, in my personal view, that there are continuing challenges is that one of the things we'd really like to accomplish, in addition to just translating a program to a machine, is to find solutions that are robust. People don't write perfect programs. Compilers don't even find perfect solutions. And the hard part is to step away from compilation as you learn it in the classroom to the real world in which you need solutions that will work in the presence of errors and incompleteness. And you'll see that theme coming up over and over again. Okay, so here are some answers. If that's the problem, the solutions are to find new compilation methods every time the world changes, to try and reuse the good solutions, and that's what many of us do in building tools that take descriptions of languages or descriptions of machines and attempt to plug in the new descriptions instead of re-implementing the functionality. One could become a language designer, design better languages. I've not taken that path. One could become a computer architect and design better machines, and I've not taken that path. But many people who have worked in this interface have discovered that because of what they know, they can now make a difference either on the language side or the machine side. Okay, so let me just put up an example, not because I'm going to teach you all over again about compilation, but just because I need something that I can keep referring to. As Fran said, the so-called front end is somewhat classical. We take a piece of text, we break it down into what linguists might call words, sequence of words. We then find the structure. That's an analysis called parsing, in which we find the phrases, if you like, the phrase structure of the program, saving only the information from the text, which is now relevant for subsequent translation. So as a little example, my tree no longer uses begin and end because the shape of the tree tells me where the beginning is and where the end is. And I'd like to, I will return to this example. Now before I do, let me get to the next step, which is the so-called semantic step. And let me distinguish what we know about the slide without the overlay from what we know after we put the overlay there. And what I've done there, if the overlay fits, is to try and sketch what you would have to do to type check this example. And the key observation I want you to carry with you is that one finds out that sum is a real variable on the lower part of the slide. One finds out that the addition is an addition, a real addition with a real result by propagating that information in the green arrows around the tree down to the bottom, and then combining the information about sum with what we know about the plus operation and so on to discover that an assignment assigns a real value to a real value. And that's what one needs in compilation in order to generate code. You need to know what kinds of operations there are. Now that turns out to be a very well-studied problem. And the interesting thing about it is that there's been some very good, more formal mathematical theoretical work. As Fran told you this morning, there had been in parsing. But in the parsing case, that work ultimately found its way into practice. And everybody uses a tool that takes a description of a syntax and produces a parser. There are tools that take a description of the type checking rules and so on and produce a type checker or some so-called semantic analyzer. And if you go out into industry, they're not in practice because the solutions never got to the point that they were sufficiently usable, that the specifications were sufficiently high level, that there was a big advantage over doing things the old way. Now, the reason I'm bringing this out is that I'm going to show you in talking about software understanding that even though this technology didn't quite make it in the compiler arena, there's a lot of knowledge there which turns out to be crucial if one wants to deal with software understanding. So that's the reason to hold on to that example in your mind. Now, let me hope that my slides are in the same order as yours. Let's go to the next slide. If it's an over, no, okay. Take the one after that. Go ahead, as long as you've got it, do it. Yeah. Okay, just to finish the story, once one has the analysis part, which says this is internally what the program says, there's a synthesis part, which in a very simple case generates code. And what I've done is to generate dumb code, which doesn't take advantage of the structure of the program. And then one uses this process Fran was talking about called optimization to discover that you can keep the value of sum in a register, to discover that adding 1 is a special case and maybe the hardware supports the special case of adding 1, and so on. So let's go on. Okay, now I started out in my research career working on compilers. I had a job as a graduate student working on compilers. And as I mentioned in my notes in the booklet, in the environment that I was in at the time I was in graduate school, writing parts of a compiler were not research. Okay? It was this dirty word called engineering. And in order to get a thesis, I was told, and all of us essentially got the message, that we had to do something that was more like mathematics. And so I wrote a thesis in parsing that had some very good theorems, and it was good. It was good theory, but in fact, I wouldn't tell you now to read that thesis, and that's one of the other messages I wanted to give to you. In a field like computer science that's moving very fast, in which technology keeps changing, the half-life of a PhD thesis is at best 5 years. In other words, 5 years later, the field has moved on, and even though you may have made a contribution, it's no longer crucial to go back and see the details. So for those of you who are in graduate school, keep that in mind when you're worrying about your thesis. It's important to find a topic. It's important to do a good job. It's not quite so important exactly what it is as it may feel to you right now, because the important part is the process and the fact that you learn how to solve new problems and to learn for yourself and to do research. And then I went on and I worked on some other things with parsing and some things that involve natural language. And then I started working on code generation because I finally felt I had enough confidence that I could try something I thought was harder. And I want to just very quickly flash up for you what the key idea was there. I don't want to teach you about it. Because in some ways this was a generalization of work I had done before, and yet by having a new point of view, it actually turned out to be very different. So let's move on to the next, and I'd like the other slide on the other projector, if I could, the one that follows that, the one that says instructions. What we had done in the examples I just showed you was to figure out how to build tools that took descriptions and produced the functionality. And we set out to do, okay, if we can put it on the other projector, it'll speed me up just a little. We set out to do the same thing with code generation, which was always done by hand. The observation was, what you're doing is a complicated case analysis. And if you can describe that in patterns, then code generation becomes a pattern matching activity, and that's an algorithmic process. It's got a formal description, and one can automate it. And so without going through the example in detail, you can see that I've described some representation of a program as a tree. I've described the instructions on a machine as a tree. And now if I want to generate code, all I have to do is overlay the input tree with the instructions and then read them off left to right, bottom to top, and I've got code generation. And so if you go through the next few examples of the input, I've got different choices for how that might happen depending on, okay, it was the other slide that I wanted on the other projector, the one that says instructions. Depending on which choices of patterns one makes, one gets different instruction sequences. And so there's one example, and I can show you I get a 2-instruction sequence. I can switch to the blue example, and I get it. You can just put it on top. That's OK. And I get a different instruction sequence because I've made different choices of patterns, and I can get to the green one and make different choices still. Now, once one has that idea, it can be used for any problem, not any problem, but many problems in which one has a collection of patterns that are tree-shaped and an input problem that's described as tree-shaped. So one can take the same idea and use it to do some of the analysis that's done in optimization. One could take the same idea and use it to do transformations. Once I've recognized that red circle on the bottom right, in fact, I've recognized an instruction. As long as I record which instruction it is, I could take what I've circled in red and simply replace it by the result of carrying out that computation. And that's a tree rewriting scheme. Now I can use that idea to take one tree and rewrite it as another tree. And now I've done a transformation on the program, which is described as a tree. And now if I do that with the goal of optimization, I've optimized the program. Or if I do it with the goal of getting a program in a different lower level representation, then I've achieved that goal. So this is a direction toward formalizing that process of compiler writing that turned out to have much more payoff than we ever expected. Now let's skip to the next methods and tools slide. I then, at some point, worked on the kinds of data flow analysis problems Fran told you this morning. I worked some on pushing this idea of pattern matching. I won't have time to show you that. And then I kept coming back to what happens when you execute the program. And so we did some stuff that had to do with timing, performance, knowing where programs spend their time. And at the same time, I kept coming back to this notion of robustness and debugging. And so let me just show you very quickly this is something we've done much more recently that has to do with debugging. And that's the following. Suppose that you have a program and you're now using a debugger interactively and you're trying to learn about the program. You're trying to understand typically why it's not doing what you believe it's supposed to be doing. One of the ways we do that is to have a user mark a certain place in the program and say, when the execution reaches that point, do something or other. Typically stop and let me see what's going on. And the way that's usually done is by picking a place in the program. Okay? Because then the technology says you can take the target program, you can find the instruction which would be executing at that point, and you can simply break the execution somehow or another. You can trap it, you can put in a jump to something. Now, intellectually, for a person, often one wants to reason about the data. And so it's often very useful to be able to watch what's going on with the data instead of watch what's going on with the control. So for example, I might want to know when a variable achieves a certain value, or I might even want to know every time I touch it, every time I read or write it. Well, think for a moment about what I'd have to do in a technology sense to accomplish that. I now have to know every time the execution touches that data object. Now the problem is that if I look at the program and try and put in those breaks, that variable, let me say count, has lots of names. Okay? We have what's called the aliasing problem. There might be a pointer to it. I might have passed it somewhere else as a parameter, and now it's the parameter whose name is visible, and so on. And if I really want to understand what's going wrong, I have to know every time that variable is touched, not every time the name occurs in my source text. So the only way one can really do that is to watch the storage location which holds that value. Okay. And because otherwise one would have to go through and somehow annotate the program in ways that we don't know how to do. And so the whole game then became a way of figuring out how you keep watching that location. Now, how do you know that that location is being touched? You look at all the loads and stores in the program, and you check whether the value that just got loaded or got stored was that particular location, or the location that got loaded or stored was that location. And once you get to that step, the challenge is, how do you do that very rapidly? Okay, and so what we did was to figure out how to do that very rapidly. Now, the other way of solving that problem would be to say, let's analyze at compile time and figure out when we know that the object that's being loaded or stored couldn't possibly be the one we're interested in. And that brought us right back to the notions of data flow analysis of programs that Fran was talking about this morning, only now we put it to a very different use. And so that was an example of ideas that I personally had worked on 10 years ago, coming back last year because we needed them yet again. And let's skip the other slides about that. And if you could just come back for 1 second. No, skip it. Let me go on to my second topic because I'm running late. This was the other thing I did in that first talk I told you about. Because I got nervous, I realized that I was running out of time when I still hadn't told them what my thesis result was. And that's not, I've learned not to do that, but I'm going to skip over some slides. Okay, and so that was an example in which the underlying issues were, how do you take a piece of text which describes a computation, figure out its properties, and then use that to translate it into another form, in that case an executable form. Now let me turn to a text which describes a computation and think about the human needs some more. And now let me remind you that when we build software, we do it interactively. And so I can consider the possibility of using a computer to help me, the person, to write programs in a better way and to read them more easily and to modify them, to edit them if you like. And so I've been spending a lot of time on that particular issue in recent years. And the idea is that when we edit a program, it's got a textual representation, and so we tend to use a text editor and modify it as text. On the other hand, we know how to do an enormous amount of analysis on those programs. It's the analysis we've been doing for years in compilation. And so if we can do that while the person is reading and writing, we can give the user feedback about what's going on in the program. And the examples that one tends to see are help with authoring, help with writing programs by having a system which tells you if you've used the wrong syntax, tells you if your types don't match, and so on. So that's a dialogue with the user about the source language. Debugging, as I just showed you, is another dialogue with the user about the source language in which the difficult issue really is how does one maintain the mapping between the source language and that executing program if, as Fran told you, one really has to worry a whole lot about optimization, as rightly so. Okay. Now, the real opportunity, and the one that I would argue is only beginning to be realized, is that one can use this same kind of interactive notion to really try and explore and understand what some formal text says that's been given to you. And this is where I thank Mary Shaw for her pointing out to you that when one does maintenance of software, much of what one struggles with is understanding what the software one has is actually about, what it says, how it works, where its interrelationships are, so on. And in order to do that, one now needs to use different techniques from the ones one uses for compilation, because the questions that people ask about programs in order to understand them are different from the knowledge one needs in order to do this mapping to a machine. And so that's one observation. Second observation is that, in fact, one has lots of time to answer questions that people ask, because the people have computers on their desks that nobody's using but them. And the amount of time that a program has between keystrokes is enormous. This is in contrast to compilation, where the efficiency of the analysis is enormously important. So because of changes in the technology, one has the opportunity to provide much more powerful assistance to people in understanding programs than we've done so far. The other thing one has in our computing environments that people aren't realizing, and Irene brought this out, is that, in fact, one can keep a lot of history. She was talking about versions and keeping previous versions of things. One can record what we as people know and discover about previous versions. One can record, for example, why certain design decisions were made, why certain changes were made. And then one can have this dialogue with people in terms of the difference between the present version and what it used to be. Skip the next slide. Now, one of the things one realizes when one starts along this train of thought is that it doesn't matter whether these languages are programming languages. It only matters that they have some sort of formal description so that one can do the analysis. One of these days, Karen and her colleagues will get to the point where we have that kind of analysis of natural language. But we've, in fact, I was just going to say, we've restricted ourselves. What she just said is the problem is that natural language utterances have more than one meaning. We've restricted ourselves in a lot of ways in order to give ourselves a more tractable problem. And restricting programs to one meaning is one of the wonderful restrictions we have. Now, from a comparison with taking compiler technology and now using the same ideas in the new context, it turns out that once again, if one asks the kind of question Irene asked about how do people work and what do they need, you discover that what's superficially the same problem is really a very different problem. Because people want to be free to choose how they're going to work. They want to be free to choose the order in which they complete something they started, the order in which they write new things. And that means that in building this kind of interactive system, one is always dealing with the fact that there's information missing. In the compiler world, if there's information missing, that's a mistake. That's a bug in the program. Okay? In the interactive world, if there's something missing, that's just something that the user didn't want to get to yet. The user doesn't want the system to keep saying, well, you didn't get to this thing yet. The user wants to remind you wants to be reminded when he or she asks that, gee, I still have this other piece that I haven't finished yet. And technically, that makes these problems both much harder and much more interesting. Let's skip a little bit to the presentation, the slide labeled presentation. And then I'm going to go to the picture after that. Okay. Now, one of the things you saw, this was actually very dramatic in Mary's talk. I wish I could have gotten up and pointed it out to you at the time. In Mary's transparencies, she used pictures. She used text occasionally, but most of the time she used pictures, even when there were graphs and charts and so on. And she even made some comments about the fact that people have used graphs to describe structure of various kinds. We use presentation, both oral and visual, to convey information to people. And we know, in fact, that when we talk to one another, we tend not to use text on the whiteboard. We tend to draw diagrams and so on. We can use computer presentation to convey information. It's a very rich medium. It's becoming richer all the time. And yet, when we go back and we deal with these formal languages, what do? We deal with text. We deal with sequence of characters. And the reasons are historical. In other words, originally, we designed programming languages using text because that was the I/O we had. We had key punches, and then we had teletypes and so on, and their language was text. And furthermore, this wonderful technology that the compiler writers developed really knew how to deal with text as an input medium. It's no longer necessary to live in that world. Okay? What the front end of a compiler does is it takes the human readable representation and internalizes it. And the better we can develop techniques to take some multimedia representation and internalize it, the more we free ourselves from having to try and understand formal documents in the form of text. And the challenge, the opportunity is there. Let me just come back to that for 1 minute. I'm going to skip this. The interesting thing about presentation is that one can describe what something looks like in a formal way. One can, I said I was not a language designer, but in fact, if you write specifications, then in fact you become a language designer again. You design specification languages. One can write a formal description that says, this is the way I want this internal notion to appear to the user. And let me go to my picture and just show, no, I'm sorry, the program presentation picture. Thank you. And then I have only one transparency after that. This is something from a project we're doing at Berkeley, and to show you what's going on here, there's a switch statement, and there are two ways of presenting it as text. In the first example, it's like a program, and the different cases are one following the other vertically. In the second example, the cases are horizontal, and there's much more use of changes in font, changes in point size, and so on. Now, I'm not trying to sell you on this particular style. I personally don't happen to like it. But the point, and what's interesting to me, is how one builds a system in which it's easy to experiment with changing the way something looks. This is exactly the same program. I've simply chosen different conventions for how it appears on the screen. If I were to go from one case to the next, I would move vertically in the first one, horizontally in the second one, and our system will do that. And the way one describes what that looks like are things like the cases will be aligned with one another, in the first case vertically, in the second case horizontally. In the first case, the cases will be indented so many points to the right of the switch, which is their enclosing structure. And the statements within the case will be vertically aligned with one another. They're horizontally aligned in the second example, in other words. So what we do is we make heavy use of annotations of the structure of that piece of text. Just as I had a tree before and I was propagating information around the tree to do type checking, now I have a tree which is a description of the picture, and I propagate information out, which in this case has to do with layout or has to do with fonts and so on. And so in the system we're building, which as you can see is the work of one of the students in the group, we're using language technology in order to describe presentation. This is text. We're using it for multimedia presentation. And we're using rich multimedia presentation in order to present languages. Okay, so there's a marriage there of what are apparently very different technologies in which we're actually using ideas, old ideas, from one side to give new approaches to the other. And I'm afraid I don't have time to tell you more about that system. So let me try and tell you what the points that I was trying to make in this talk. I've tried to show you that one of the reasons that what we in the language community do is interesting is because there's lots more going on in what I'll call a linguistic object than its text. Now that, in fact, is a point that Karen made about natural language as well. I started out by telling you that language translation is interesting because the world keeps changing. What we discovered in doing this project we're doing now, and some earlier work that my group did, is that interactive formal language processing is a different problem from compiling. And therefore, although you can take certain ideas from the one side, since you have a different problem, you need different solutions. And then finally, by considering this interactive realm, what one learns is that language technology can be used for lots of things besides compilation. And therefore, even though compilation is a so-called mature technology, there's lots of work and lots of opportunities for the research community. So, thank you. Okay. I've been told there are 2 minutes for questions. Fran.
Okay, this isn't a question, it's a comment. It's something I want to put on the record. Sue has made many great contributions, but I don't think anyone really recognizes the contributions she's made to establishing the standards for our science and languages and systems. When Sue became the editor of TOPLAS, Transactions of Programming Languages and Systems, our scientific papers are mostly appearing in a few conferences and here and there. And she established that journal, and she was an editor of it for many years. And in the process of, as an editor, she really established the scientific standards for that part of our community. Thanks very much, Sue.
Thank you. There's a mic coming your way.
Yes, when you were talking about software understanding, I have a friend back at the University of Virginia who's currently working in industry for the summer trying to understand a very large program. And I was wondering that she didn't write, that was written by other people and changed by other people, of course, also. I was wondering if any of the tools that you're working on are possibly to address this kind of problem and what stage they're at so I could possibly point her toward them.
Yes, that's certainly one of the problems that we're working on. And I mean, there are two parts of it. I suggested in talking about history that the more you can capture, the more you might have in the future, but the world isn't always like that. And so one of the things that we're trying to do is to help people to figure out how to understand some large system that they didn't write or that they wrote 5 years ago and don't remember anymore. The best way to find out about it would be for her to send me electronic mail. I'm graham@cs.berkeley.edu.
I have a question about your comment on the list about interactive language processing not being interactive compiling. Mm-hmm. It seems like to some extent debugging is a link between interactive language processing and interactive compiling. And I wanted to know if you could make some comment about how it would fit in between the two things you were talking about.
Okay, what I said about interactive language processing is that the kinds of questions one wants to ask, the kinds of analysis one can do, aren't necessarily restricted to executable languages. And therefore one can get a lot of help with non-executable specifications and things of that kind. When you have execution, as you do for programming languages, then the problems become even more interesting because there's a lot of knowledge one can have about the language. Karen actually knows this because she's working on some of these problems. You could know a lot about what questions to ask in some sense by knowing more about the source program whose execution you were trying to understand, and we don't have any tools that do that at all. On the other hand, you have to keep mapping back to the state of the computer at the time you've interrupted the execution. And that mapping problem, of course, restricts what you're able to do, the kinds of questions you're able to ask about the execution and get reasonable answers.